Okay, we're going to pick up where we left off and talk a little bit more about errors and how there are different types of errors. If we understand where these different errors are coming from, then we can either control them or react to them and adjust for them, or at least quantify them. And so it's very important for us to think through what the cause of the error is, identify it, and then quantify it. So errors prevent us from knowing the true value, right? If we're measuring something with a tape measure instead of micrometers, there's going to be some error associated with that, right? It's the wrong instrument, or maybe it's just not a precise enough instrument. And I think a lot of times as engineers, we're trying to select the right instrument. And uncertainty analysis is at the core of figuring out what is the right instrument. How accurate do I need to know this? How accurate can I measure this with the equipment that is available to me? What is my confidence in the result? And then what is the interpretation of the data that I have collected? Okay, so let's dive right in. Number 1, bias systemic. Number 2, precision random. 3, illegitimate. And 4, additional errors. So let's dive in and talk through each one of these. Okay, bias and systemic errors. You can see this little dot I've got off of the target, and this is to just help keep that in mind, that these bias errors are always going to be an offset or a shift away from the true value, and those could be due to calibration, recurring human errors, defective equipment, loading resolution limits. And so these bias errors or systematic errors are always going to shift what we're seeing through our instrumentation and our measurements. They're going to shift them away from the actual value every single time. And it's going to be pretty consistently off because of that bias that the instrument or the human is applying to the data that's being collected. Okay, so now a couple of examples here. We've got zero shift and sensitivity. And so a zero shift means that we have shifted the 0 point one side or the other. And so instead of starting at 0, we're now starting at 1, or maybe we're starting at -2 or something like that. So we've got this zero shift or null error offset. We also have maybe a sensitivity. Maybe the slope of the line is not correct. And so when we get a value, when we read a value in, then our output value is now off by a certain amount because our slope is incorrect. So that would always cause it to be systematically biased in one direction, away from the true value that we're trying to measure. So again, calibration, recurring human, defective equipment, loading, resolution limits. So resolution limits, if you remember, we had the little guinea pig sitting on top of a scale, and that had a plus or minus of 1 gram, 0.1 gram. And so that is the resolution limit. We cannot see what's happening between 0 and 0.1 grams. And so that's a resolution limit. Now, the reason I have these asterisks here is because sometimes these can manifest as a bias or a random error based on conditions. So it's important to keep in mind some of these recurring human errors, defective equipment, resolution limits, they could be a bias or they could be random errors depending on what's happening in the conditions. So we'll talk a little bit more about that later, but just for a quick example to help you get your head around it is a recurring human error. What if I measure it every single time? Maybe I'm looking at it with a parallax error because I'm looking at the bottom of the meniscus, say on a temperature or a thermometer. Now, if I had 30 different people look at it, some might look at the bottom, some might look at the top, some might look in the middle. And so we're going to have a random error instead of just a bias because I'm going to read it from the bottom of the meniscus every time. So those are kind of one quick example of how those three could be presented as a systematic error or a random error. Okay, so now let's dive into precision and random errors. So again, on the target over here, you can see that I've got these red dots indicating that the data that we're collecting is all around the true value. of what we're trying to capture. And so this is random. Things are happening randomly, and there's a precision associated with it. So again, equipment disturbances, fluctuation in experiment conditions, fundamental accuracy, error of sensors, sample resolution. So how quickly are you sampling to collect data points? And again, we've got those others here that can manifest either way. A lot of times though, this is an important one, stem from insufficient sensitivity of the instrument. And so if we have an instrument that maybe has a scale that is much larger than the signal that we're trying to measure it, it might not be sensitive enough. And so we're going to have random errors all over the place in that one. Okay, illegitimate errors. This is one that we love to write in our lab reports, but they're illegitimate. The experimenter making a mistake. I see it all the time. I don't know why my data is junk. My data didn't work out. Something happened and we didn't realize that there was an offset. We didn't realize that our data was incomplete. Those are just mistakes, and mistakes can be fixed by going back to the lab. So illegitimate errors, you shouldn't put them in there. Computational error after an experiment. So maybe you've got it in an Excel spreadsheet, you put in the wrong equation and it kicks out something wrong. So that's just illegitimate. Now here's the last one, additional errors that can appear as bias or precision. This would be, there's a pretty long list here, but I've just narrowed it down to 3. Backlash, friction, hysteresis, calibration drift. And so maybe you've calibrated something and over time, because of temperature, or maybe there's several other variables that could be in there, your calibration is drifting away from what the true value was. Also errors from variations in procedure among experimenters. I think there's probably a lot of examples that could be added in here. And so I just added this little picture in here so you could see backlash is if you were to turn this screw back the other way, there's this little gap here, you would have that much play or backlash in it, just so you can get a feel for it.